Once again, you are welcome for the second meeting. So this is actually a program that is organized by NUXA China, and it's on advanced data analysis in R. So yesterday we actually started about some introduction regarding some basic understanding of how to import data, how to import data of different kinds, and even what else did we learn? So we kind of learned a bit. So if you've not actually watched that video, you can actually watch it from either the YouTube or the NUXA China page. So for today, we are going to the next phase of the presentation. For those who don't know me, my name is Clement. I am a final year PhD student studying mathematics at Cardiff University, and I'm also a Vice Chancellor Scholar of the university. So without wasting time, I'll just share my screen now. Just a minute. So I'll share the screen now. All right. Okay. I hope you can all see it. Okay, so like I said, today is the second session. So we are left with 2 more days of programming. What are the objectives for today's study? So today I'll try and wrap up and finish within an hour. So I'll speed up a little bit. And most of the things we are going to talk, I have more advanced versions of them on the YouTube channel. So don't forget to watch, and then don't forget to subscribe to the channel as well. So most of the examples we are going to consider here are technically something we call toy examples. By toy example, I mean simple examples so that you can easily understand the things I'm going to talk about. But you can get more information on YouTube, and you can download all the YouTube scripts also from Piazza, just in case you've not subscribe to the Piazza as well. And everything is free, so just take advantage of that. All right, so today what are we going to talk about? So the general motivation is we are going to talk about loops and how to use apply functions. Loops and how to use apply functions. These 2 class of functions are very useful, especially when we want to now create our own algorithms. We even want to create simulation algorithms. We even want to create complex functions to implement some specific tasks. So please try and mute when you join. All right, so that's the general aim of the loops and then apply functions. Okay, so for the loops, what they do is that it's all about, there are instances where you want to do some operation iteratively. I think there are a bit of, okay. All right, so I can go ahead. All right, so I just muted everyone. All right, so basically when you talk about loops, it's all about situations where you want to do some operations iteratively. Okay, so by iteratively, there are instances where you are doing an operation for different values of, it could be different values of some index, it could be different values of sample size, it could be different values of anything. And then sometimes too, you are doing some recursive form of calculations and computations. So the whole goal of looping is just to do iterative, or to solve some problems iteratively. That is all. And the looping can be a bit complicated. You can actually have a single loop, and you can have even double as many loops as possible. So keep in mind, how many loops should we consider? It depends on how many possible combinations you are trying to consider. So if you look at those who are into statistics, there's this particular field of statistics called design of experiment. And you realize that in design of experiment, they have this experiment, which is more like a full factorial design, where we are considering different possible combinations. So when you're actually using a loop, you cannot, for each specific loop can represent, let's say, one particular operation, or let's say one particular variable of interest, or set of variables of interest. And then, so if you have 4 or 5 things that you want to look at their possible combination and how they affect the overall outcome of a model or whatever you are interested in, then it implies that you're going to have as many loops as like almost 5. Okay, so just keep in mind how many loops are you going to consider is dependent on what you wish to do. If you want to consider possible combination of just two items, then you are going to obviously use a double loop. For this presentation, I'm going to restrict myself to single loops. When you go on onto the YouTube videos, you find out examples of, I think, double loops and so on. And then I told you I created a very complicated function, and within that function, that is used to do a lot of summary statistics. Today, I'm not going to talk about that. It will be talked about tomorrow. But you find out that we used a lot of loops in there, and then we made use of some apply functions as well. So today's class is just going to be a good introduction for you, so that when you see those advanced or complicated functions, you know what each is trying to do. All right, so what are we going to talk about specifically for the objective? So we are going to first of all talk about for loops. Initially I said with conditions, but this time I took away the conditions because I didn't want to repeat myself. I've already done most of these things on YouTube, so I'm trying to approach it from a different point of view, so that there wouldn't be any form of monotony, or let's say we just want to avoid repetition. Okay, fine. So the next one is we'll look at how to use a while loop. So the while loop, so anything you can use for loops for, you can also use while loop for. At the moment, I don't expect you to understand any of them. We understand very soon. And I told you that looping is a form of iterative procedure. And each procedure, you can actually save the results for each iteration. And then, so how do you save the results? There are so many ways you can save the results. You can actually save the results as a group of vectors. You can even save it as a list. You can save it as a data frame. You can save it as a matrix. There are so many ways. Even as a vector, for instance, there are so many approaches you can actually use. So always it's advisable you stick to which one is convenient to you. And the next thing, we'll just look at a bit of introduction into simulating probability distributions, and then how to do some plotting with loops. The reason why I'm going to talk about the simulating probability distribution is that I want to also let you understand that looping is not only used for functions. You can actually loop over a plot. You can loop over so many different things. So keep in mind that everything we are going to see is not the final. It just indicates that there are a lot of other possibilities you can consider. So just keep in mind that we can also use loop to actually plot several plots at the same time, iteratively. All right, so let's continue. Now, there is this disclaimer I made. The disclaimer is that avoid loops if not needed. Avoid loops if not needed. What do I mean by avoid loops if not needed? Let me just create a simple reason here. So for instance, let's say I'm creating a vector, let's say a vector x. And let's say the vector is, let's say, sequence of numbers from 1 to 100. If I want to find the sum, I can just use sum around the vector x, and then I have the sum. But imagine this was done within seconds, isn't it? But someone wants to complicate their lives, and then the person wants to stick to looping. I will explain the basic, how do you call it? The basic form or structure of loops. But I just want to explain something here. So the person just went straight ahead and made something complicated like this. I don't want you to understand anything at this stage. I just want you to have a look at why I'm saying that avoid loops when it's not necessary. So I'll explain everything shortly. So the person wants to just find some, and then maybe the person writes, let's say, total, and set the total to 0. And then they go on and says total equals maybe total plus I. Now, if they should run this one, it also gives a total. I just feel like in this case, it's not necessary doing the looping, because just using the sum function actually gives you the results. So this is what I mean by avoid loops when it's not necessary. It doesn't mean that loops are super necessary, that you're always going to need it, especially when things start getting complicated and you have to do some iterative procedures. But what I'm saying is that avoid it when not necessary. Okay, so for instance, this one is not necessary to use loops when you are summing, when you are adding, and all sort of things. But for the sake of today's presentation, I'm going to use a basic addition as a toy example. All right, so now we just, like I said earlier, so I've created a vector. So yes, yesterday, I'm sure you by now you should be familiar with the sequence function. So I created a vector from 5 to 1000, and I'm saying that the length dot out equals 30 means that I want to generate 30 different 30 numbers from 5 to 1000. And then I'm also generating another 30 set of numbers, but from 1 to 150. This is just, and then with that, I'm increasing it by 5. So I want the regular increment to be 5. So be familiar with some of the arguments of the sequence function. So with the sequence function, you can specify the first value of the sequence, the last value of the sequence, and indicate how many observations you want to produce. So that is what I mean by length.out. I want to produce 30 numbers between 5 to 1000. You can actually produce 30 numbers between any two limits, right? And then with this one, with a y, I was generating sequence of numbers from 1 to 150, and I'm saying that it should increase. There should be a regular increment of 5. So it meant if we start with 1, the next one is 6, and so on and so forth. Fine. So here, all I needed to do was just to do addition. So by just considering x plus y, I told you yesterday that it does element-wise addition. So in this case, it produces our results for it. So this is basically, so what it does is it picks the first value of x and the first value of y, then it adds. Then it goes on to the second value of x, the second value of y, and it adds. That's what I mean by element-wise. Okay, fine. So with this, you don't need a loop for. But now we are just going to, and keep in mind, you can always run your numbers to any decimal place you're interested in. So for instance, using, and yesterday I explained the use of the print function. So technically, we could have just typed the object name without this print function, and it gives us something like this. But yesterday I said the print function is a bit much more organized, because if you look at the print function, it kind of organizes your output for you. So I usually would prefer that, especially if you want to explain to someone else. Okay, fine. And then we use the run function here to run any decimal number to any decimal place. Okay, so here I'm running it to 2 decimal place, and then I'm printing it out. So if I should put 0 here, then that is the nearest whole number. If I should put 1 here, it means 1 decimal place, and so on and so forth. Fine. All right, so now let's start the actual looping. Now, so this is the basic syntax. Every function has a syntax, right? So for the loops, this is the syntax. So first of all, you are going to start with, this is the for loop we are starting with. You are going to start with for, and then we'll bring this round bracket, because I told you this round bracket basically indicates argument, right? So once you bring the round bracket, there should be something in there, and whatever in there are arguments. Now the syntax is that you consider anything. So here I'm saying that anything in a sequence. So the sequence is what you want to consider iteratively. So suppose you are doing an experiment, or you are doing you are fitting a certain model, and you need to obtain, let's say, 10,000 different possible results. Then it implies my sequence is going to be from 1 to 10,000. So the length of the sequence is dependent on how many iterations or repetitions you want to do. And then whatever is in the sequence, you can use any symbol. Here I type val. Next, you see I can use I. So I in a sequence, you can use any letter or any variable in that sequence. And then you can bring your curly bracket. The curly bracket can be avoided if you want. That is if you have a single operation you are trying to loop over. But there are instances where you are looping over a lot of information, right? So in that case, you then bring the curly bracket so that you can type as many information you want to repeat over across all the possible values of the sequence. Okay, so now let's start. So already we created a variable. Okay, so I created a vector x. Okay, that's not necessary for now. All right, so here, if you remember, I created a variable x. Now this variable, keep in mind that there are two ways of knowing how many elements are in x. So you can actually type length of x, and that will give you how many elements in there, which is 30. So one thing I just wanted you to understand is, from the basic syntax, we said we are always going to consider a certain variable in a sequence. Now that sequence has a specific structure. It should always start from 1 to a certain limit. So it meant you can actually consider 1 to the length of x. Suppose I want to loop over all possible values of x, then how many sequence should I consider? I can use 1 to the double is it column? Yeah. So that double column sign, or the column sign, technically indicates 2. So 1 to that would generate a sequence of numbers from 1 to 30, right? Now I wanted you to note that if you just type sequence, if you just type sequence along x, okay, it also does the same job. So why would we stress ourselves trying to bring 1 to length of this? So I just want you to know that you can either go by this approach, 1. So always in your loop, it should be 1 to your for loop, it should be 1 to a certain limit, or you can use sequence underscore sequence along s, and that also returns the indexes or the positions of each element or number in x. Okay, fine. So now let's so we are going to repeat what we just did here. What we just did was basic addition, adding vector x and y. Okay, now we are going to use loops to do this, and it's going to be very necessary and useful in the sense that this variable x you are seeing could have been a complex function. It could have been even a simulation model. It could have been anything. Okay, so I just want you to know that we are using this as just a toy example, and then you can get other more complex examples on the YouTube channel. Fine. So here, suppose you want to use loop to do the addition. Okay, fine. So I've already told you that you don't need loops to do addition. Okay, but here we just want you to learn how to use loops in general and how to store the results of loops. This vector x and y we are seeing could have been, let's say, a function. It could have been a plot. It could have been anything. So just keep that in mind. Fine. So how do we save results of loops? So keep in mind that I said the loop is an iteration or iterative procedure, and at each iteration we can save the results as either a list, a vector, or even a data frame. Now here we are going to save it as a list. I'm sorry, as a vector. Now, as a vector, there are ways we can go about that. So, for instance, let's say I type. So keep in mind there's a function in R called numeric. If I put any number there, it will generate numbers, or I mean zeros, and the zeros will be, the length of the zeros will be dependent on the number that I specify. So if I specify 5, it's going to generate zeros 5 times. So keep in mind that numeric is a way of creating zeros. So if I put, let's say, 100, then it creates 100 zeros for me. Fine. Now, why do we need to create these things? We create these things as something called a holder. So keep in mind that if you want to save each result of a loop, the first thing you do is that you create something like a holder. So it's more like you have a book and you want to save the book or put the book somewhere. If you don't have a shelf, okay, how would you place the book? So the holder is more like creating a form of let's say a space where you can save the results. You get it. So that's basically the principle behind the holder. So, and there are so many ways you can actually, so I can technically create a sequence of zeros to save each result. So if I specify 100 here, then it implies I have 100 different iterations that I need to do. I could have also used something like replicate, let's say NA 100 times. Okay, and this one will replicate NA, like not available, but so in R is technically representing missing values. So I can also replicate NA 100 times. You can actually use anything you want. So I can even use my name. So we see some of the examples. I use my name as the holder. So meaning that the holder is just create anything that at the end of the day, the loops will go and replace those things that you created. And in order to create that holder, it could be sequence of zeros, it could be sequence of or different, or let's say sequence of NAs, it could be sequence of anything, even true or false. So I could have also considered replicate false. Let's say I just type false, or I can even type true. And all these are ways of creating a holder for if you want to save it as a vector. So if you want to save it as a vector, there are so many ways you can do that. Just stick to which one actually best fits you. So here I'm just going to present all the possible ways you can go about them. So fine. So keep in mind that we've created a sequence of zeros. How many zeros are we creating is depend on how many loops. So the vector and keep in mind, you can only add two vectors if they are having the same length. So here X and Y are having the same length. So it meant I can use any of them to represent or to compute the length. I can use any of them. So I could have used Y here. I can also use X here. So numeric of the length of X actually returns a number of zeros, and how many numbers is equal to how many observations are there, which is 30. Fine. So the next thing you do is that you start with for I in sequence along. I told you sequence along S is the same thing as generating sequence of numbers from 1 to how many observations are in X. So I could have replaced this one by 1 with the column sign, then length of X, and it will do the same thing for me. So all you need to do is that you write for, you open your bracket, I in this sequence. Now the holder, which is sum underscore loop 1, you just open or you just create this square bracket around it, and you put the I in there. Suppose I had used K, I would put K here, and I would also have put K here, and it should do the same job for me. So like that's why I was saying that you can use anything. You can even use your name instead of K or I. Fine. So here all we are doing is that what we are saying is that now sequence along S. Let me just run the sequence along S for you to see. So the sequence along S is actually returning the indexes or the positions of each number in the vector X. So what it's doing is that it first of all takes the first number, which is 1. Then it extract. I told you the square bracket is used for extraction. So it meant when K is 1, it is extracting the first value of X. When K is also 1 here, it's extracting the first value of Y. Then it adds them. Then after adding, it goes to replace the first 0. So here, when K is 1, it goes to replace the first 0. So if you had used NA or anything, then it also does the same thing. It goes to replace that holder. Then it now goes on and start from when K is 2. Then it does the same thing till it gets to when K is 30, which is the final number. So that is basically what is going on there. So keep in mind, so looping is not anything that is very difficult. So the secret is that always you have to have some variable in a sequence, and that sequence is dependent on how many iterations you want to do. Fine. So what we just did was saving it as using a sequence. I mean, saving the iteration as a vector, and then for each vector, we were replacing the zeros, which were the holders instead. Fine. But now, suppose, like I said, I could have used my name instead of zeros. I could have used my name, or you could have even used false, like I said. So if I use my name, what happens is it's the same thing. I've not done anything to the previous. I only changed the numeric to my using replicate. Replicate means it should repeat my name how many times? 30 times, because the length of X is 30. Now, what happened was, if I do that, it returns the same results anyway. However, you could see there's some quotations around the numbers. Anytime you see quotations around anything, it represents that particular output is a string or a character. So if you remember yesterday when we were creating a vector, I said is, so for instance, if I want to create, let's say, names 1. If I want to create names, I use the concatenate sign because I want to create a vector. Then I said if I should type maybe my name here and type, let's say, this one, you are going to get an error. But the very moment I bring the quotation, the quotation signs, and we don't have any error. Okay, so keep in mind that anytime you have a string is names or something which is not a number. Okay, try and make sure you bring the quotation, okay, around it. Fine. So using my name, it's also doing the job. Okay, if I just replace this one by NA, it actually prints what I wanted for me. Okay, so I can even put 0 there, and it will also do the same job for me. You can actually use the replicate instead of the numeric. It's also doing the same thing. Now let me go back to my name. So here I use my name here, but it was printing out the results, but with some quotations. So, and that means that it's seeing it as a character. How do I know it's seeing it as a character but not a number? You just bring class around that object. Class around this one is telling me it's a character. Now, if I want to return the numbers, I just have to bring as.numeric, meaning that treat it as a number, and then it actually prints out what I wanted. But I think that's just a long process. Why not just put 0 here? Why not just put, I could also put false and false, and it will do the same job for me. Okay, so just keep that in mind. Fine. So here at this stage, I was trying to save it as a list. So what we've learned is how to save your iterations as a vector. All these things will uncover very soon, especially from tomorrow onwards, because you realize that these are just the building blocks that we need to be able to do the more complicated stuff. So to save as a list, all you need to do is that you just type. So instead of typing numeric of let's say creating sequence of zeros or sequence of NAs or whatever, you can just type list and open this argument without putting anything there. Or you can use null and you can use this C with the open brackets, kind of. So, and so the only difference is that here we're using, when it's a vector, we are using a single square bracket. When it's a list, we are using a double square bracket. So keep that in mind. So when I use list and I run, you realize that what do we mean by list? It meant you get each result will be numbered. Okay, each iteration will be numbered. So you realize that we have series of all the results there, but they are numbered, and that's what we mean by list. So if I want to extract the first number, I just need to bring double square bracket and put 1 there. That will extract the first one for me. If I put 3 there, it will extract the second one for me, and so on. For vectors, you can still use a single vector to extract, a single square bracket to extract. But keep in mind that it is only for vectors. There are instances you get errors if you are doing something which is much more complicated. So just to be on the safer side, use square bracket to extract from list. Okay. All right. So let's continue. Fine. Suppose I should replace this one by C, which is the concatenate sign without anything. It's object. What did it say? Oh, I use C. The concatenate sign is small letter C. All right. So if I use the concatenate sign, I also just get the numeric directly. Okay. So keep in mind that's also another way of saving as a list. I can also use now, and it also does the same job for me. So just keep that in mind. Okay. Let's go on, because we don't have time. Now for the while loop. The while loop is a little bit different from the for loop, but it's doing the same job as the for loop. Now, for the while loop, what we need to put here is that instead of the for loop where we had considering a certain variable I in a sequence, this time around you rather put a condition that if let's say the iteration, let's say if I is less or equal to, let's say 30, it implies that the while loop should do the iteration. When it gets to 30, it should stop. If you fail to put any condition here, you are likely to get something called indefinite loops. Indefinite loop means that it's a loop which is unending. It doesn't end. So be careful. That's not the only way you can get indefinite loop. I'll show you another instance. Fine. So for the while loop is also similar to the for loop, but what we are doing is that instead of starting with I in a sequence, I write the first value of I outside. I just write I equals 1, meaning that I want to start from I equals 1 and continue to I equals 2 and so on. But where should I end? I just put when I is less or equal to length of x was 30. So I'm sure you are seeing the difference. Unlike the for loop, we consider I in a sequence from 1 to 30. This time around, I'm rather saying that while, so here what we are saying is that while I is less or equal to 30, it should do some operation for you. Okay, so meaning that once is anything greater than this range, then it stops. Okay, fine. So it starts with when I is 1, so it asks, is I less or equal to 30? Yes. Then it does the addition and it saves it in this results. Don't forget here too, I'm saving it as a loop. As a list. And as a list, I use C, the concatenate sign with a bracket open. I could have used null, as I explained already. If you forget to bring this last line of code, you get an indefinite loop. It will not end. Maybe you can try it. When it happens that way, you just have to shut your R and then open it again. So what this is doing is, this is where the iteration, without this one, the iteration would not hold. What this is saying is that when I is equal to 1, it should ask, is I less than 30? If so, it should do the addition and save it in the list. And then we should now consider I equals I plus 1 means that the first I was 1. It should now consider I equals 2. And then it should start the process and ask whether 2 is less or equal to 30. And then when it's done, then it comes to when 2 plus 1, which is 3, and it does the process repeat recursively. Now, don't forget, if you ignore this one, you will get an indefinite loop, which is an unending loop, meaning that your code will never end. It will take ages. It will not end if you run. So when it happens that way, don't forget to close your R and start again. So this is where the iteration actually occurs. Without this, it doesn't hold. So that's just the difference between the while loop and the for loop. Now, I told you that we can actually also use loops to do some plotting. How? So first of all, I'm going to introduce probability distributions. So what we mean by probability distributions, I have another session on YouTube where I've extensively talked about these things. So I'll just give a brief summary. So keep in mind that probability distributions are just they are random variables, but just to make it easier, they are just used to describe a phenomenon or some random processes. Okay, and keep in mind every process in reality follows a distribution. If I ask, if you want to know, for instance, there are 100 women who are going to deliver. They can give birth to either a male or a female. One thing you have to notice that the number of women who give birth to, let's say, females, if females are your interest, actually follows a binomial distribution. That number of women who can give birth to females actually follows a binomial distribution with some parameters. I wouldn't go into the parameters. And then Poisson distribution, for instance, if you are looking at the number of road accidents, or let's say the number of events that occurs within some infinitesimal amount of time, or for instance, let's say I want to look at the number of accidents that occurs every 1 hour at a certain junction, or every 1 hour in Ghana, or every 1 hour in UK, that follows a Poisson distribution. Uniform distribution is a way of just saying that if all things being equal. So it's a way of actually sampling, or it's a distribution that actually gives equal weight to each observation in a way. I wouldn't want to go too much into it. Exponential distribution too is also a very useful distribution, and is very useful when it comes to simulating stochastic processes, especially when you are doing Markov chains, which I won't even go into this. Normal distribution is technically the most important distribution ever. Why? Because if you've heard of central limit theorem, you can actually watch, but is it the third YouTube video? You find more about these things. The log normal is just a log transform of the normal distribution. Fine. So here, what I'm doing is that I'm just going to simulate a data. So what is the essence of simulation? Suppose you've heard that, because I told you that the number of, let's say, road accident occurring, let's say, in Ghana every 1 hour follows a Poisson distribution. So suppose I know the average number of road accidents to be, let's say, 20. Okay, average number of road accidents to be 20. I can actually simulate, and let's say I want to simulate 100 occurrences, okay, of that. How many road accidents that will occur within that interval of time? So let's say I want to simulate that, and then I know the mean to be let's say 50 road accidents occurs. So suppose you don't have a data. What this is doing is that it's trying to give you a form of artificial data that should be able to mimic the kind of data if you actually had it in reality. So simulations help us to be able to get artificial data or generate artificial data, that especially when we don't have access to the actual data set, but we have information about some parameters. So for instance, if you know, then, and keep in mind, if I should run this one at the moment, you are seeing, if I should run this one again, if I should run this one, you will get different set of observation. That is what we mean by randomness. So it implies that anytime we run this, we run a random generator, it gives us different output. If you want to get something that will remain fixed, just for reproducibility sake, you just put something called set.c. Okay, you can put any number in there. You can put any number here. I'm putting 1. So if I should put 1 here, what it implies is that if you run the same function on your computer, you should be able to get the same results as I had. Okay, you should be able to get the same things here. So that's the essence of set.seed. And if you've realized, there are a lot of people who do publication and then the journals will say that they are not able to reproduce their results, especially when in their model there were a lot of randomness, such that anytime you run the model, you get different set of outcome. In that case, it's always advisable to do your modeling at a specific seed number. Sometimes some seed numbers will give rise to good results. I don't think there's any optimal way of identifying which seed number is okay. But you can just set any seed number so that in future, if people want to reproduce your results, especially when within your algorithm you have a lot of randomness, as such that anytime you run, you get different set of results. Set the seed number for reproducibility, just in case people want to reproduce your results. Don't forget that. All right. So here, what I'm doing is that I've first of all considered prop distribution equals now, because I'm trying to create a list. And I told you, so I can actually save some output in a list without necessarily putting a loop around it. Okay. So here I'm saying that the index 1, the first one should be 1, and that should correspond to the binomial data. Okay. So the binomial data, I'm simulating 5,000 binomial data with some specific parameters. You don't need to understand all these. This is just for it's just a toy example. You can further watch the YouTube videos, and everything will be uploaded as well. So don't try to understand everything within the 1 hour period. Fine. So here I've simulated a binomial sample, a Poisson sample, uniform exponential, normal and log normal, 5,000 of such samples, and I've saved them in this list. One beauty about list is that I could even use letters or any name. So I could have written binom here, and I could have also written some specific names. Let's say let's say this is Poisson. I could have written that. Let me take this off, and let me delete this. And let me just to make life simple, let me consider just the first one. So if I should run prop this, and then I bring binom, so meaning that this is now like an object, but it's in a form of a list. It will still give me the results I'm looking for. So keep in mind that the beauty about lists is that you can put any specific argument you want, whether a string or a number, to make life. But keep in mind, if you're going to use a for loop around them, you definitely need to use a number, because you definitely need to use a number. So don't forget that. That's why for this example, I'm using a number here. Fine. So we have simulated the data. So at the moment, this is where the for loop becomes handy when you are doing these plots. So what I want to do is that I want to look at what is the distribution of each of these probability distribution. How do they look like graphically? So, and to do that, I also want to choose different colors for each of them. And then, so what am I trying to achieve here? So all I need to do is that I'm using for j in sequence along. I told you, keep in mind here, the names prop distribution is a vector, but it's a vector of strings. But it doesn't, but the very moment I use sequence along that, it was sequence along, let me copy that. The very moment I use sequence along this, it returns 1, 2 up to 6. Yeah, because I told you sequence along actually returns indexes. It doesn't return the actual element or the actual entries. It returns their position. So you can actually use this one as a more natural way of doing your for loop, instead of, and alternatively, I could have also considered 1 to the length of the names, and that should also give me the same output. Okay, fine. So I'm using sequence along that, and here there's a function called hist, and that is what we use to do histogram plots. Okay, so what I'm doing is that, and every function has an argument, and those arguments you cannot write it anyhow you want. It's only when you create your own function, then you can specify the argument to be anything you want. But if it's an inbuilt function, it has been written in such a way that you have to go by it, right? So it meant if you want to choose colors, the inbuilt function is saying that the argument for color choice is COL. Okay, so you cannot use, if you use any other thing, suppose I use, let's say I wrote color here, I'll get error. Okay, so keep that in mind. So keep in mind, if it's a default, or let's say if it's an inbuilt function, you have to be able to, or you are using a package. The package has some specific arguments. Don't use your own argument, or else you get errors. Fine. So here I'm considering each probability distribution. When J is 1, it considers the first probability distribution. It does histogram plot of it. And here the colors, I am indexing it by J. When J is 1, it will choose the first color, which is red. Okay. When J is 2, it will choose the second color. That is for the second probability distribution. And then paste. So the paste here, what I wanted to do is that the very moment you type paste of, let's say, color, it actually pastes each of the entries, each of the was I using color? I said names. The names were binomial, Poisson, and so on. So what it's doing is that now if I should run this one, to maximize the plot, I need to run that. Fine. So if I should run this one, now it does the first plot. Let's say it plots the first distribution and it chooses the first color, and then it pastes the first name. Okay. And then the x-axis, I'm saying that it should be called samples. If I want to label the y-axis, I could have also add y label equals, let's say, frequency. I could have also added that to it and also run. Okay. So these are some of the ways we do histogram plot. So just keep in mind, at least you've not started data visualization, but this is just something for you to know that you can actually loop around or over plots. Okay, so keep that in mind. Fine. And then what's the essence of the parMF row? This one is to specify how many rows and columns. So I'm plotting it says different distribution, and I'm saying that I want them to be on 3 different rows and 2 columns. Okay, if I had specified, let's say, if I had made this one 1 by, let's say, 6 by 6, I mean, we are going to get something like this, which is not useful. So keep in mind, I always it's advisable to make the number of rows more than the column. Suppose I have made it 2 by 3. It meant I want 2 rows, 3 columns, and I'll get something like this. And I don't think this is also very useful. So always let the number of rows at least to be more than the number of columns. You can have a 9 by 9. Suppose you are plotting 9 at the same time. So this is the beauty about R. You can actually plot as many graphs as you want, and then you have some nice plot like that. At the moment, I just want 3 by 2 because I have 6. Fine. Now let's go on to the next. With this, it wasn't about looping. I was just trying to demonstrate a certain statistical property that if you plot 2, so here we've generated 100,000 numbers from a normal distribution with some specific mean and standard deviation. And I did the same with another normal sample, but they are large. There's this theorem that if you should plot these 2 large normal samples, you get something that is elliptical, like a sun. So yeah, I was just trying to demonstrate that to you, that anytime you plot very large normal samples, you get something that looks like a sun. If you reduce the sample size, the degree of the elliptical shape would decrease in terms of its intensity. So in this case, you don't get something very handy. So I'll just stick to the previous one. Fine. So this is just to demonstrate that theorem for you. Now let's start with the. It will take a bit of time. So now let's start with the apply functions, because we have less than 70 minutes. I want to wrap up. I want to speed up a little bit. Fine. So with the apply functions, what are they used for? They are also very useful. Let me just come down. So these apply functions are very, very useful. So all these things we are doing, they are going to serve as building blocks for the complicated statistical analysis we are going to be doing. So once you are familiar with these things, then when you see apply function in my complicated summary statistics function, then you know that, oh, okay, this is what we are trying to do. Now we have different types of apply functions. The most important ones are what I've highlighted here. So we have the lapply function. And what the lapply function is used to do is that it can actually do the same thing as looping. So the for loops that we're doing, we can actually use apply functions to effectively and or efficiently actually also loop over any iterative procedure we want to do. And sometimes they are faster than the for loops, but it depends on the problem. There are instances where the for loop might be faster than it, but most of the time the the lapply functions tend to be faster than the for loops. Fine. Now the sapply is also a form of lapply function, but what it does is that the lapply will return your results as list. For lists, I told you it implies for each iteration it will number your output, right? So it will number the output for each iteration. That is what we mean by list. So that if you want to extract each of them, you use a double square bracket and you specify any index. If you specify 3, it means you want to extract the third list. Fine. But what the sapply does is that it actually returns the lapply results as a vector or matrix depending on the complication of the problem. So if this one is just so suppose this one returns a list from, let's say, 50 lists. This one will return a vector with the sapply to return a vector with the same size 50. Okay, so that's how efficient sometimes the sapply can be. Okay, because it kind of summarize or wrap up your lapply functions. What's the use of the tapply functions? The tapply functions, they are instances where you are trying to compute, let's say, the means of, let's say, your data, your numeric variables. You want to compute the mean across some categories. For instance, let's say you have GPAs of students, and for the GPAs of students, you have their specific GPAs, and you wanted to find, let's say, the average GPA between males and females. So the tapply function helps you to be able to find any summary measure, whether mean, median, anything you want. You can even create your own summary measures, and then it does that for each specific factor or categorical variable you want to consider. So that's how we're able to get, let's say, some summary measures for some specific categories of a categorical variable. So keep that in mind. That's for the tapply. And what does the apply function does? So all these are called class of apply functions, but there's another function called apply. So what that it helps us in a way that we can compute some summary statistics for numeric variables either across rows or columns. There are instances you want to compute. Let's say you have 10 different numeric variables, and you want to be able to find the mean for all of them. You don't have to find the mean separately. So it meant you could have just found the mean separately for each variable. That is waste of time. With the help of the apply function, once you specify that you want to compute the mean across columns, it will compute the mean for all of the 10 numeric variables at the same time for you. Okay, so that's the beauty. And then the last thing is about parallelization of codes. This is where the actual complicated programming actually begins. So there are instances where you are looping, but for each loop, it takes a lot of time. When it happens that way, and keep in mind that as at this stage, everything we are doing now is only running on or is only running on a single core or a single processor of your computer. So keep in mind, some of us might have, let's say, a computer with 7 processors or 7 cores. Some are even having supercomputers with so many cores, like 64. So there are instances where you are, especially those of us into simulation, our simulation algorithms can sometimes be very complicated for each iteration. When it happens that way, you wouldn't want your simulation or each iteration to run separately. Or so for instance, when I is 1, it will consider only 1 core. Then it has to finish all the results of that particular iteration and goes to the next iteration with the same 1 core. That can make your algorithm super slow, especially when each iteration takes a lot of time. So what the parallelization does is that, suppose you have, let's say, 10 cores, you're able to set your cores in such a way that all the 10 will run at the same time, and each iteration will not affect the speed or the computational time of the other. So that is what the parallelization actually does. So it's a way of trying to run, instead of doing the iterations one at a time, like first iteration before the second iteration and so on, you can actually set it in such a way that it does all the 10 iterations the same time. It doesn't finish the first one before you go to the second one and so on. It's doing all of them in parallel. Okay, so the parallel approach actually speeds up your code a lot of time. So I have some algorithms which used to take me, let's say, 7 days for me to get the simulation output. After applying, let's say, parallelization, okay, for it to run on multiple cores, then I can get the results. Something that I was getting the output in 7 days, I can now achieve them in, let's say, 20 minutes. So that is how much it can be useful, especially when you are doing complicated stuff. All right. So if you recall, we use for loops to do addition of these. If you remember, maybe I didn't talk about that, but keep in mind that instead of x plus y, you can also use sum with the x comma y, and it does this. Keep in mind the sum function is such that it can sum. So the sum function of xy, okay, is the same thing as the sum function of, so here in this case I'm summing all the how do you call it, all the elements in x and y, but this time around I'm indexing it by position such that it should sum, just let's say when I is 1, it should sum the first entry of x, the first entry of y, and it's the same thing as just saying that it's the same thing as just saying xi plus yi. So keep that in mind. It's doing the same thing. Fine. Now, how would you use lapply to do? Look at how complicated for loops structure looks like. Now, let's look at the lapply. It's just a line of code. So for the lapply, you specify the index. So the sequence along S is the same thing as 1 to 30, if you remember. And then you just have to bring a function I. Here I can use k. If I use k, then I'll also use k here. Okay, so keep that in mind. Fine. Now, if I should run this one, it also does the same thing that the previous one was trying to do, especially when we're saving it as a list. So this one also saves your output as a list, as I said, but it's very effective because it's just a single line of code and it's doing the same thing as the for loop. This function here could have been a simulation algorithm. It could have been any complicated thing. So this line of code is, so keep in mind that you could have had a very complicated function, and this line of code will still do the for loop using the lapply. The lapply, especially when the model or whatever you are considering takes a lot of time, most of the time is much more faster than the for loop. And even the for loop, we also have its parallelized version called for each. So there's a function called for each in R that can also be used to parallelize your for loops as well. So there are so many things. You just stick to which one is convenient for you. So you realize that the lapply actually return each results as a list. If I replace the L by just using S, meaning that sapply, you realize that it returns as a vector. So this is what I meant by the sapply tries to wrap up the lapply. So if it returns this kind of list, it will return it as a vector. If the lapply returns, let's say, double list, this one will return it as a matrix. So that's the difference between the lapply and the sapply. Fine. So generally the sapply could be faster than the lapply in a way. Fine. So now let's look at computational time. There are instances you are doing a simulation or you are comparing between different algorithms, and maybe you'll be interested in your computational time. Here, I'm just trying to let you know that the lapply function and the sapply function can sometimes be faster than the for loop. Okay, so here I am creating I'm generating a data from a normal distribution, but at different sample sizes. So first of all, I'm generating, let's say, 10,000 different samples from normal distribution. Here I'm generating 300,000 and so on and so forth. This is over 90 million or something. Fine. Here I just wanted to see how fast the for loop would actually, the computational time with the for loop, and also the speed of the lapply and the sapply. Fine. So here, and keep in mind that the for loop, when you have a single operation, instead of using so you realize sometimes I can bring a curly bracket and take this one down here, and maybe bring a curly bracket here, right? I told you always bring a curly bracket is useful. But when you have this, but if the block within this curly bracket, if you have a lot of operation going on, okay, then you need to always bring the curly bracket as you are seeing. But when you have just a simple line of code there, I can choose to ignore the curly bracket and it will still give me the results. Okay, so that's basically why. So here I was just trying to show you that you can actually write the for loop also as a single line of code for it to look as simple as what the lapply and the sapply is trying to achieve. Fine. Yeah, so here what we are doing is that we are generating normal distribution at different sample sizes, and then I'm using this function, this proc.time, is a way of trying to check the time. So you have a starting time, then the end time is actually the current time minus the start time, and it gives me this output. Keep in mind that the user time and the system time, the sum of it is actually equal to your CPU time. And usually that's what you are interested in, not the time elapsed. So keep in mind the sum of these two are usually what represent the amount of time your CPU actually used. For those who be comparing between the computational time or speed of different methods, keep that in mind. Fine. So here, I just did that using a for loop. I did the same thing using lapply and check the time. So you realize that here it took almost, let's say, 8.442 seconds. This one took 8.0 seconds. It tells you a little bit of the difference. I mean, but it's not very significant. When I use the sapply, you realize that it took 7.8 seconds. And yeah, so keep that in mind. Now, if I had parallelized these codes, keep in mind that the for loop, the sapply, lapply, they are all making use of only one call. And I told you that there are instances where you have a very complicated algorithm that you might have to, or complicated model that takes a lot of time. And suppose you are using method. If you go to my YouTube channel, there's one aspect on jackknife and bootstrapping estimation technique that I actually have covered. Is something very useful. You need to actually watch and learn and practice. You realize that it's also especially bootstrapping, you need to use for loops. Now, suppose there are instances where the algorithm is very complicated. It's going to take a lot of time. So in such instances, you would want to be able to set your code in such a way that it should run in parallel. So if it is 10,000 iterations you want to do, you don't want to start with the first iteration for it to finish before you go to the next iteration. That will take ages. You want to parallelize it. Okay, so here, what I've done with the sapply and the for loop, I'm going to use the same for what? I'm going to parallelize those codes. So whatever you're going to see here is actually, you can use it for any complication. So keep in mind that this same code, you can use it. So this function of k with the R norm, you could have had a complicated function and it will do the job for you. Okay, so keep in mind that you can actually use this code and make your function as complicated as anything. Someone is writing on, fine. So keep that in mind. Fine. So now with the apply function, with the parallelization, I told you we have two ways of parallelizing. Either you use the mclapply, or you have something you call parLapply. So to parallelize, we have either parLapply or mclapply. But there's a disclaimer I want you to keep in mind, so that when you get errors, you don't run to anyone. You should be able to solve this error. The mclapply is much more effective than the parLapply. And the mclapply only works on Linux machines. Those of you using the MacBook and those of you using Linux. Someone will ask, is it useful to, or it is good to run, let's say, run R on Windows machines or on Linux machines? Technically, both are okay, but generally, using Linux has an extra advantage. It has a lot of advantages. Even if you look at the graphics, if you plot something on the Windows R on Windows, if you look at the quality of the graphics, no matter the resolution you set, you realize that on the Linux, there's a bit of difference. The Linux machines, they kind of give much more, for some reason, they give better graphics, fine. And then keep in mind that mclapply only works on what? Works on Linux machines. That is if the number of cores are more than one. It can work on Windows only if you set the number of cores to be 1. Then in that case, it will ignore the mclapply and stick to the original lapply function. So keep that in mind. But the parLapply doesn't work on Linux. It only works on Windows, but it's a bit complicated. This mclapply is so easy to implement. However, it's also faster than the parLapply, but it works only on Linux. On Windows, unless you use only one core. So what I did was that you realize that if I should ignore the MC here, the function that I have was the same function for the lapply. The only difference is that for the mclapply, there's an extra function called mc.cores that tells you how many cores you want to consider. So for instance, you need to install this package called Parallel, and that package is what we use to parallelize our codes. I'll need about 5 minutes to wrap up. Fine. So we use this function called detect calls, and that detect calls able to detect how many calls your computer has. So there are instances. I mean, for this, I'm having only 4 calls anyway. But when I'm doing more complicated stuff, I use my school supercomputer, which has 64 cores. So in that case, I can even set my cores to, I can set the cores to be 16, and it can use 16 of the cores. So imagine if 4 cores would take, let's say, 1 hour to achieve something, setting it to 16 would take, let's say, 20, would take, let's say, 10 minutes. So keep that in mind. Okay, fine. So here the only difference is that it has an extension called mc.call. So it's the same thing as the lapply function. But you realize that here I'm using 4 cores. So I wanted to do the looping using 4 cores, and it gave me an error. I kept this error for a reason. Look at the error message. Anytime you get error, look at the error message. The error message is saying, what the error message is saying is that mclapply greater than 1 is not supported on Windows. So that's what I was saying, that the mclapply, I mean, the mclapply only works on Windows if you set the number of cores to be 1. But setting the number of cores to be 1 is the same thing as using the lapply function. So in that case, there's no need to use the mclapply if you're going to set the number of cores to 1, because it's technically using the same lapply function. Fine. So here, that's why I'm getting the error. Those who are using Linux, you can copy and run this and you will not get any problem using Linux operating systems. Okay, so here, if I want the mclapply to work, all I needed to do was to set the number of cores to 1. However, for some reason, it's still faster than the lapply function, even when I set it to 1 to run on only 1 core. Because if you look at the lapply function, the computational time was let's say 8 seconds, and then this is like 7.91 seconds. Keep in mind, you will not see significant difference depending on how complicated the problem is. That is when you see a very significant difference in the computational time. Operations where the computational times are not very intense, I mean, you might not see such the significant difference in there. So keep in mind, there's no use using mclapply on Windows. It's not useful. Fine, but you can still use it if you set the number of cores to be 1. Keep that in mind. Now let's go on to the next. So you get access to all these codes. The video is being recorded. It will be uploaded on YouTube as well, and then you can watch and practice at your own pace. To use the parLapply is a bit complicated, but that is strictly for Windows users, and there are a lot of Windows users than Linux users, I suppose. So what you first of all need to do is that you have to make clusters, and the cluster, this is the code you need to do, and then the num call was the number of calls that was detected, okay, which is this one. Okay, so this one detects and the number of cores. So if you want to know the number of cores on your computer, even this function in R will let you know how many processors you have. Fine. So let me go straight to the parLapply. Where were we? Fine. So the first thing is that you have to make clusters, and after making this cluster, the next thing you have to do is that, so suppose your function has the global environment in your function. Keep in mind, there's difference between global and local environment, or global and local variables. When I create a function, the objects inside the function that I created, they are called local variables or local objects. But if I run anything, so for instance, sample size is not within a function, right? So it's something I created outside a certain function. So this is what we call, this is example of the global environment. I mean, sorry, a global variable. So you have to, in order to be able to use the parLapply, you have to be able to specify all the variables in the global environment. So for instance, index, this index that I've created 1 to 30, or 1 here, the sample size is having I'm considering 6 different sample sizes, so the length is 6. So the index is 1 to 6. Now this 1 to 6, the index, object index, is outside a certain function, so it's a global variable. So I have to specify it here. Sample sizes was also a global variable, so I have to also specify it here. So if you don't do that, you get errors. So keep in mind that in order to parallelize codes in Windows, you have to make sure your global variables, okay, you actually what declare them as I've declared here. So there were only two local variables, which were index, which is this one. Two global variable, which was index, which is this one, and sample size. They are something outside the function. They are variables that are outside the R function. So in that case, you need to declare them. All right, fine. So there's nothing much. The only difference is that the mclapply, the number of cores was specified at the end, as you saw. But with this, you specify the number of cores at the beginning. Okay, but in this case, you don't use the number of cores per se. You use the clusters. This cluster is equivalent to the number of cores, but you have to do that in order to be able to do that on Windows. Fine. And then this index is I'm considering 1 to 6, where the first one corresponds to the sample size, and so on and so forth. Fine. So when I did this, so you realize that the mclapply, I could not use more than one core because it works on it for more than one core. It only works on Linux. Now see the difference. This is giving me 7.91, even though I thought it was fast. Now with the parLapply, because it's on Windows and I could use several cores. I could use 4 cores. Okay, it's actually running under 3 seconds. So that is the beauty about the parallelization. So you can see that it ran within 2.3 seconds compared to the other ones, which were 8 seconds and so on. You will see significant difference if you have a very complicated whatever algorithm. Let me just go on. I'm wrapping up shortly. So here we wanted to use the tapply and then apply function. As I told you, that class of apply function, there's also another one called apply, which I've already explained. So here to do that, I'm just importing the data. So yesterday we set a working directory. If you remember, we set a working directory, and then we imported a data called meta rate. This is a CSV file. Now we know how to import any data. So at this stage, by the end of this 4-day seminar, you should be able to work with any data structure, be it SPSS, SAS, any data. You should be able to import. So suppose you were previously used to Minitab or SPSS, or let's say SAS data, or let's say Stata. You should now be able to import all the previous data set that you had and do the analysis in R. Okay, so don't forget that. Fine. So here we've imported this data. We want to use the apply function. Now the apply function, this is the function. This is how we specify. So the data here, how many numeric variables do we have? The first 1, 2, 3, 4, 5, 6, 7. These are the numeric variables, okay? And then the last one is the only categorical variable there. Keep in mind, you cannot find means of categorical variable. You can only find means, standard deviations, and those numeric measures. You can only find them based on a numerical variable, okay, or a quantitative variable. So here, I extracted, so I told you if you want to index a data frame, you use a double square bracket, but you bring a comma. A comma here, this part is, so for instance, let's say I want to extract just the first row of the data. I'll put 1 here, and I won't put anything here. This will extract the first row of the data. Suppose I want to extract the first 3 rows of the data, I can also use this. Okay, so you get, so that's so the first position corresponds to rows, the next one corresponds to columns. So suppose I want to extract the first 3 rows, but the first 3 columns, I'll rather do this. Okay, so keep that in mind. Fine. So here I extracted the numeric ones. Technically, I think 7 is also part. Fine. So if I should now specify here margin, the difference with the apply function here is that if you specify the margin to be 1, it will compute any function you specify across each row of your data. But usually you want to consider columns because the columns represent your variables, right? So in this case, you set it to 2, and then it finds the mean. So here, the function I want to use is mean. I want to find the mean for all the numeric variables, and it does all of them for me at once. I don't have to find each of them separately. Fine. So here, I use the print function, and the print function will obviously give me an output that looks much nicer. Fine. Anyway, so when you consider the margin to be 1, it finds this mean across each row. We had about 43 rows, so it finds the mean across each row, and so just know the difference. So keep in mind that 2 is what you would want to use if you want to find for the actual variables. Fine. So here I created my own function that should return let's say, the mean and the variance. So I just want you to know that you don't have to necessarily use only inbuilt function as an argument. You can use any function you've created. So here I just created a simple function to return both the mean and the variance. Okay, and here I specify the function as I am calling it mean underscore variance. I specify that function, and you can see that for each numeric variable, it computes the mean for me and it computes the variance for me, and then it goes on to the next one as such. So keep that in mind. So keep in mind you can use any function you actually create to do that. I told you the last time that the dollar sign is used to also extract. So at the moment, if I should extract, let's say I should bring the dollar sign with the rate and I should extract the results with that, it will just extract the variable corresponding to rate. I mean, the results corresponding to rate for me. So if I should put, let's say, LFP here, it will extract the mean and variance corresponding to that for me. Okay, fine. So just keep in mind all this can be done. The T applied, I told you that it is used to find, let's say, the mean, the variance, whatever you want to find across categorical variables. So all you need to do is that, but keep in mind that you can only do that one at a time. However, if you want to do it across several variables, you can write a for loop around it. Okay, so keep that in mind. So here I'm just trying to find the mean and variance for the variable called rate of crime, and then I want to find it for both those who are either in the southern part of the region or not. So yes means the no means they are the no means they are not from southern. The yes means they are from the southern region. So if I want to obtain the mean and variance for each category, we use the tlapply function. So at this stage, you should be able to do some basic data analysis using any data set. I mean, so if you've already signed up to Piazza, you have access to a lot of data on the Piazza page, the resource session, and then you also have a lot of codes and examples on YouTube as well. Fine. So that is basically all that I needed to talk to you about today. So just to wrap up what I just did for today, we are done. So today, all we did was to expose us to looping, and we said looping is very useful, especially when you want to do iterative procedures. And these iterative procedures can be done based on any complicated functions. Okay, so here I even wrote a disclaimer that keep in mind that the loops can be used for more complicated functions or complicated tasks, such as simulation. In simulation, it could be Monte Carlo simulation, stochastic simulation, it could be plotting different items, and even more complex functions. Okay, so here I was using the addition as a toy example. Fine. And we also learned that we can also use lapply and sapply function to literally do the same thing that the for loops are doing. And we also said that the for loop can, the while loop can also be used to do the same things, things similar to the for loop. However, the syntax is a little bit different. So keep that in mind. And then we said that to parallelize your codes, why do we need to parallelize our codes? Maybe you've not gotten there yet, but the time is coming. You'll be running some models and it will take a lot of time. And keep in mind, anytime you run in R, at the moment, it is using one core. It will always use one core until you tell R to use more than one core. So keep that in mind. R would always use one core, and not just R, any software, any programming language. It will use only one core until you tell the programming language to use more than one core. And keep in mind that to use more than one core, it is only when you are doing some form of iterative procedures. Okay, so when you are doing iterative procedures, that is the only instance you can tell the computer to run on different cores at the same time. So keep that in mind. And so the iterative procedure could be 10,000, but you can tell the computer to do that with 10 cores than using only one core. So if it is using 10 cores, then it means it will take the first 10, takes the next 10, and so on and so forth, iteratively like that. Fine. So just keep that in mind. So that is just the end of today's lessons. Tomorrow will be much more complicated anyway, because this is just the building blocks. For tomorrow's session, we are going to now do creating functions. So today, I didn't want to really expose you to how to create functions. Tomorrow, we will learn how to create your own functions. So for instance, you want to find correlation. Suppose there are certain tasks you are going to do in future which does not have inbuilt functions, but you know a formula for it. If once you know a formula for anything, you should be able to create your own function to implement that. So keep that in mind. So yeah, so tomorrow we'll learn how to create our own functions to do anything we want to do. and then that is it. So see you tomorrow, and I'll end today's meeting at this point. And don't forget that everything will be uploaded on YouTube. There you get access to all the codes, the data, everything that we've been using for this we are going to use for this 4-day event. You have access to all of them. I'll upload all the script on Piazza as well. If you've not joined, if you've not enrolled onto Piazza, it's free. So because without joining, you will not be able to download. That's the only problem. And then in order to join, you just have to send me your email address, and then I'll send you an invitation link. Once you follow the process, you should now be able to have access to all the materials at no cost. So on this note, I will end here. Thank you very much, and see you tomorrow. Okay.